Hello everyone. Today let's talk about a project titled Hybrid Intelligence Based Crisis Action Guidance Platform. Crisis situations such as natural disasters, conflicts, and large scale emergencies pose serious risk to civilian safety. During crisis, people receive a large amount of information from government alerts, humanitarian reports, and local announcements. Much of this information is time sensitive, fragmented, or contradictory, making it difficult to act safely. Thus, there is a critical need for systems that provide clear, conservative, and time aware guidance. This project focuses on supporting civilian decision making by converting volatile crisis information into safe action guidance. The statement of the problem is crisis information is fragmented, time sensitive, and often conflicting. So, civilians face uh, outdated or unreliable updates during decision making. An existing system such as broadcast alerts do not support safe decision making. So the objective of this project is to build a safety oriented decision support system that converts volatile crisis updates into clear, conservative and time aware action guidance to reduce confusion, cognitive load and secondary civilian harm without prediction or automation. The scope of the project includes processing verified crisis updates, handling time decay and uncertainty, generating conservative action days, and our target audience are civilians and humanitarian agents. Our deliverables are rule based guidance engine, ML assisted confidence module, action output interface. Our functional coverage include processing structured crisis updates from verified sources, handling time-sensitive information using expiry and decay rules, managing uncertainty and conflicting updates, and converting information into simple action states such as safe to stay, safe to move, seek aid, avoid area, and wait for update. Our system boundaries and deliverables are as follows. Our project operates in near real time with minimal delay, no personal data collection or surveillance, no predictive or autonomous decision making. So the final deliverables include rule based action guidance engine, ML assisted confidence evaluation module, zone level action output interface, and system documentation. So this is the methodology of our project. First and foremost is data collection. We collect the structured crisis updates from verified sources such as government advisories, humanitarian reports, and local alerts. And then we normalize the data by standardizing incoming updates by validating format, location, category, and timestamps for uniform processing. Then the time decay management. We assign expiry duration to each update and automatically discard outdated information to prevent unsafe guidance. And then we evaluate the confidence. We assess the reliability of updates and detect conflicting information using ML assisted confidence scoring. Next is the decision logic and guidance generation. First is rule based action inference. We apply the deterministic safety rules to convert process information into predefined action states. Next is zone level aggregation. We combine multiple updates within a zone to generate a single conservative action output. Next, it is the guidance delivery. We present the action states such as safe to stay, seek aid, avoid area, or wait for update through the user interface. Next comes the testing and validation phase. During this phase, we test the system using simulated crisis scenarios to verify correctness, stability, and safety under uncertainty. This is the architecture diagram. First is data sources such as government alerts, humanitarian reports, and local announcements. Then the data ingestion and normalization phase. And there is the backend processing going on and action inference engine, and then guidance output and ethical safeguards. And this is the design use case diagram, which shows the graph of active set of use cases enclosed by system boundary. Our main three actors are government or data provider, civilian user, and system administrator. This is the design class diagram. And this is the sequence diagram. And this is the entity relationship diagram. This is the data flow diagrams, level 0 and level 1. Now we can see about the algorithm used in our project. First and foremost, we use time-aware information processing algorithm. In this algorithm, we receive structured crisis updates with source, zone, timestamp, and category, and we verify the update format and normalize data for consistent use processing. Next, we assign expiry duration to each update based on its type and severity. This is called time to live or TTL assignment. Next comes the expiry check. If the current time exceeds TTL, mark the update as expired and discard it. Next, we active. Next is the active data collection. Only non-expired data updates are forwarded to further analysis. The purpose of this algorithm is to prevent outdated or unsafe information from influencing decisions. Next, we use the rule-based action inference algorithm. First is the confidence evaluation. We assign reliability scores to active updates using ML-listed analysis, conflict detection, identify contradictory updates within the same zone, and then rule application. We apply predefined safety rules based on severity, confidence, and conflicts. Next, action state mapping. We convert the results into action states such as safe to stay, safe to move, seek aid, avoid area, and wait for update. Next, zone level aggregation. We generate a single conservative action per zone. The purpose of this algorithm is to provide clear, explainable, and safety first guidance without prediction. And these are the hardwares and softwares involved in our project. Hardwares include server or cloud based system, standard computing hardware such as CPU, memory, and storage. No sensors or specialized hardware are required. Works on existing infrastructure. And the softwares are programming language such as Python, backend framework such as Fast API, and custom rule based logic, rule engine, ML libraries such as Scikit-learn, NumPy, Pandas. Database are SQLite and PostgreSQL. API format is REST and deployment using web, mobile, or SMS interfaces. The implementation of this project is done using Python as the core programming language. The system used multiple Python modules for data ingestion, time handling, and rule evaluation and action generation. Structured crisis updates are provided through manual input or API based sources in JSON format. Each update is validated, normalized, and assigned to time to live or TTL value. A time decay engine automatically discards expired information to prevent unsafe guidance. A rule-based decision engine processes active updates and determines the appropriate action state. Machine learning libraries are used only to estimate confidence and detect conflicting updates. The final output is a single conservative action per zone displayed through a web or API interface. These are the important core segments. First is the crisis ingestion Python 5, and here we have the time decay Python 5. Next is the output formatted Python 5. And now we can see about the output of our project. This first screenshot shows us the homepage of the project, which serves as the primary entry point to the crisis action guidance platform. It prevents users with presents users with clean and structured interface designed to minimize cognitive load during high stress situations. The interface displays the platform title, system status, indicators, current time, and ensuring that users are immediately aware of the system's operational time. And this is the map-based visualization of the project. The platform provides a map that helps users to understand the spatial context of the crisis zones. And next is the real-time update handling. The platform dynamically updates guidance as crisis information is received. When a valid update is processed within a defined time window, the system revises the action state accordingly. Next is the alert notification output. Alerts present concise and actionable messages that include the zone identifier, action state, and essential instructions. These notifications ensure timely awareness while maintaining the platform's core principle of conservative guidance. And these are the test cases under which your project are tested and validated. Here we have five different test cases with input details, expected results, and action result. And finally, if the test case is pass or fail, as we can see, all the five test cases have passed. And next we have here another five test cases for, that is tested on system performance, stability, and safety validation. Finally, the results of the project. The proposed system was evaluated during predefined crisis scenarios to validate decision logic and time-aware behavior. The time decay mechanism correctly filtered outdated crisis updates and ensuring guidance was based only on recent information. The rule-based engine generated consistent and conservative action states across different crisis situations. And in scenarios involving conflicting inputs, the system prioritized safety-oriented actions such as avoid area and wait for update. The overall system response remained stable and deterministic during all test cases. And the SDG goals of a project are crisis safety and civilian protection, and SDG 3 good health and well-being, SDG 11 sustainable cities and communities, in SDG 9 industry, innovation and infrastructure, and SDG 16 peace, justice and strong institutions. So, conclusion, the hybrid intelligence based crisis action guidance platform provides a safe, time aware decision support system that converts the volatile crisis information into clear and conservative action guidance. By combining rule based logic with MLS uncertainty handling, the system helps reduce confusion and secondary civilian harm during emergencies. The future works include by extending the by integrating GI-based visualization and additional real-time data sources for improved situational awareness. And one other future enhancement that may include multilingual support and broader deployment through mobile and public alert systems. These are the references we use for our project. Thank you.